So now that we've finished the system side of our diagram, so we've covered the system, the modeling, and our system modeled. So our systems are basically the behavior of our systems. We've modeled them using label transition systems and cryptostructures. And this is our final system models we have. So we've done the right hand side. We now move on to the left hand side, which is our requirements. How we formalize the requirements and get property specifications. So we're going to do this in this lab using propositional linear time temporal logic, PLTL. So temporal logic is a special type of model logic where the truth value of assertions varies with time. LTL is a type of temporal logic that uses mathematical language for describing linear time properties. LTL operates across all possible path executions of a system model and verifies that each of them satisfies the formal specification. Now you notice that we've gone from PLTL to LTL, but they're essentially the same thing. It's basically linear time temporal logic that uses propositions. It's the same. Note that it does not branch off at any state to determine every possible path available from that state. Instead, every state has a unique successor, and it ensures over a single linear computational path that a property is satisfied. And LTL cannot express possibility properties. So let's go through this bit by bit. So, temporal logic, a special type of model logic where the truth value assertion varies with time. This means that, let's say, something is not true today, but tomorrow it may be. So if you think about it as, it is not your birthday today, but over time, this assertion will change. Eventually you will come to a day where it is your birthday, so that assertion goes from false to true. That is what we mean by it varies with time. LTL again is a temporal logic that uses mathematical language for describing linear time properties. So these are basically the formulas that we're going to show you of how we can actually describe these properties. LTL operates across all possible path executions of a system model and verifies that each of them satisfies the formal specification. So LTL doesn't skip any path, it goes through every possible path. But it is different to CTL. It does not branch off at any state to determine every possible path available from every state. This might be hard to understand because we have not done computational tree logic just yet. But just know that we are ensuring over a single linear computational path that a property is satisfied. So you can see here that there's no branching off. So every state has one possible successor in our path, in this specific path. So in this specific path, you can see that black is a successor, and yellow is the successor of black, and orange is the successor of yellow, and so forth. In our next run, on the same model, again black was the successor of red, but now brown is a successor of black, and green is a successor of brown. So before it was yellow, but now we've taken a different path, and we're going down from black down to brown. We're doing this linear path. And the next one, green is a successor of red, with this light blue the successor of green, and purple the successor of this light blue. But they're all single paths. They're all separate linear paths. You'll see in CTL that instead of having, we go from red to black to yellow, and from here red to black to brown, we'll have red to black, and you'll have two split paths from black, one going to yellow and one going to brown. And then we'll have multiple paths splitting off from here and from here, and you'll get a tree-like structure. And that is the difference. So temporal logic consists of two primary set of operators. Logical operators, which we've seen in the previous lab with our decision diagrams and decision trees and Boolean logic. So we have our not operator and or implies and double implies, if and only if. You can find these at our link again on the SCCE YouTube channel at this playlist. But what we want to focus on is our temporal operators, which are denoted by G, F, U, and X. These are symbols that represent what they do. This gives us a BNF, Backus normal form, for the construction of LTL formula, where P ranges over a set AP of atomic propositions. So this AP just stands for atomic propositions. So you may be wondering what BNF is. So it stands for Backus Nauer form, or Backus normal form, is more commonly known. And basically this is the syntax that is used to define the LTL formula. So from this syntax we can compute any LTL formula that is possible. And it is almost the smallest form you can have. You can also have positive normal form, where you would actually have every possible type of syntax. But Backus normal form would basically be the exact defined syntax for the construction of this LTL formula. It is commonly used with computing languages and instruction sets, communication protocols. So I ask you to research on your own Backus normal form. But for now, all you have to know is from this syntax set we can construct any LTL formula. So our formulas we have true, we have P, so the atomic proposition P, which can be true or false. We have not of this formula. We have formula 1 or formula 2, next formula, formula 1 until formula 2. And we want to ensure that these are satisfied, this formula is satisfied. Or phi is satisfied if you want. We call it phi and psi. So let's go through our temporal operators, G, F, U, and X. So F means in the future, also denoted by this diamond shape, or eventually. This basically means a property is satisfied at some point in the future. So if you see F of phi, F of our formula, or property, if you wish, it basically means true until this formula, or phi. So what this means is, you'll notice that f of phi is not in our BNF syntax for LTL. However, we can achieve it using true until phi. So we could use this formula. Replace phi 1 here with true, and phi 2 will be whatever we're trying to prove here. Now true in this instance means essentially we don't care what atomic propositions, what formula is there at every state. It is inconsequential to what we want. All we want to know is that phi is satisfied at some point in the future. Until then, we don't mind, we don't care what any formula is, whether you countless other atomic propositions that are true or false, it doesn't matter. We're just trying to determine that this formula is satisfied at some point in the future. So that's what F means. Again, we will have questions on this in the next section, to show it more concretely. G stands for globally, again for this open bracket, close bracket, kind of square symbol, and you can also commonly known as always. So G of phi is not, eventually not phi. So basically this means a property is satisfied now and forever. So when you say G of phi, or G of the formula, we're saying this atomic proposition always holds. This formula always holds from now until forever. Another way of saying that is, if you saw here, this eventually, if f of phi, a property is satisfied at some point, you could also say that a property is never satisfied at some point, or never not satisfied. Sorry. So never not satisfied is the same as always satisfied. So you see again, we do not have g of phi in our B and F syntax, but as we saw here, we have not of f, not of phi. We can already determine f of phi using true until. So if we just say not true until not phi, we can get g of phi. So now you can see how you can combine all of these instructions to get f and to get g. So you don't actually need to put f and g into the B and F form, because you can actually derive it through the operations we have already. So x is basically our next. It's also sometimes denoted by a circle. So this means our formula or property is satisfied at the next transition. Actually, I'm just going to call them properties from now on. I know I've been calling them formulas and sometimes atomic propositions, but we're going to call it a property. So a property is satisfied at the next transition. So if we're at state 0, and we want to know if, let's say, going back to atomic position white, is it true at state 1? Then we say x white and see if we're at state 0, is white satisfied at state 1? If it is, it is. If it's not, it's not. Now x is part of our B and F, so we don't need to derive it in any other fashion. Next is u, which is until. So we have phi until psi, or as we see in our B and F, it's just phi 1 until phi 2. That's the same as phi until psi. This must mean a property phi is always satisfied until it is not, at which point another property psi is satisfied. So if we say p until q, p is always satisfied. So p until it's not. Then once p becomes false, q must become true. That is what this basically means. Until can be either strong or weak. So you can have strong until or weak until. When you don't see the u in this instance, it is assumed you're using the strong until, also denoted as s of u. So phi s of u psi is the same as phi until psi and f of psi. So this basically means, so psi strong until phi means that the first property psi must always be satisfied again until it is not, at which point the second property psi must be satisfied. The second property, which we see here, and eventually psi, means the second property psi must eventually be satisfied. This means you must always find the second property in your model. So you can't just have phi true forever. This property cannot, the first property cannot remain true forever. You must be able to find the second property. Otherwise it is not strong until. That is what strong until means. However, in weak until, we'll see that phi until psi, or always phi. So the first property can always hold. Or you can find the second property, and if you do find the second property, then the until comes into it. But it is not necessary in weak until. So we got phi weak until psi means that the first property must always be satisfied, and the second property may eventually be satisfied. At which point, if it is found, the first property must not be true, must not be satisfied. If the second property phi is never satisfied, so you never find this, then the first property must always be satisfied. So this is this part. So let's go through the difference between strong until, weak until again. In strong until, the first property must remain satisfied always until it meets the second property, at which point the first becomes false, the second one becomes true, or whatever you're trying to prove, and eventually, so you always find the second property. Otherwise it is not strong until. In the weak until, the first property can always remain true. You do not have to find the second property. However, if you do find the second property, then the first property must no longer be true and the second property must be true. So that is the difference. So that is our f, g, x, and u. So you got eventually true. It's going to be satisfied at some point in the future. Always true. It is satisfied now and forever. Next, the property is satisfied at our next transition point. And we got our until. We got our strong until. Satisfied until it finds our second property, and it must always find the second property. Or weak until. Satisfied until it finds the second property, or you never find the second property, and the first one is always true. They are our LTL properties.